Hello friends, now we are going to discuss here the unit number 3, that is the functions and relations. So we are going to discuss here important points which may be asked for examination purpose. So the very first point, which is seen on your screen, properties of binary relation. So basically there are 5 properties of binary relation. First one is the reflexive, second one is the symmetric, transitive, antisymmetric and irreflexive. So whenever in the university examination, if there is a question, properties of binary relations, so you have to first of all list out these properties and explain one by one. So what is meant by, first of all, reflexive property? So see here what is meant by reflexive property. For example, a binary relation R in the set X is called as a reflexive for every X belongs to capital X relation R, that is ordered pair X comma X which is belongs to capital R. That is nothing but the reflexive property. Means, for example, I am explaining or I am briefing over here. For example, let us consider capital X is equals to 1, 2, 3. Capital X is equals to 1, 2, 3. That is the set given to you. Then when the given set having one relation R and that relation having some ordered pair 1, 1, 2, 2 and 3, 3. Because as it containing 3 elements 1, 2, 3, it should be mapped with ordered pair X comma X such a way that it will gives you 1, 1, 2, 2, 3, 3. Then and then it is called as a reflexive property. Whenever there is a single pair, 1, 1 is present, it is not said to be reflexive property. All the all the pairs of the same type should be present. That is 1, 1, 2, 2 and 3, 3. Reflexive. Then next one, symmetric. For example, if R is the relation and which is mapping from, you can see here, X, R, Y, and it having another mapping from Y, R, X, then it is called as a symmetric property. Then it is called as a symmetric property. Then transitive property, you can see here, if two relations are given to you, X relation Y, Y relation Z, then it gives you X relation Z. Okay, it should give you X relation Z. It is not correct. It's wrong. It's a correct X relation Z. Okay, means what? X relation Y, Y relation Z, then it should give you X relation Z. So that is nothing but the transitive property. Then next one, we are going to discuss here irreflexive property. In the case of reflexive property, so what we are going to do? In the case of reflexive property, if one node is there, then there is a, for example, if one node is there, then there is a, it's not working, just wait. If there is a node, then there should be loop at that particular node. Fine. So that is the reflexive property. Or in the terms of matrices, all the diagonal elements should be present, or all the diagonal element having the value as 1, then it is called as a reflexive property. And in the case of symmetry, if X relation Y is there, then there must be Y relation X. Then in the case of transitive property, if X relation Y, Y relation Z, then it will gives you X relation Z. That is the transitive property. Then talking about irreflexive property. In the case of irreflexive property, there should not be loop. For example, like this. That is the reflexive property. That is the irreflexive property. Keep in mind that at the same time, no relation gives you reflexive as well as irreflexive property. Okay, so it may be gives you reflexive property or it may be gives you irreflexive property, but it cannot gives you reflexive and irreflexive at the same time. And the antisymmetric, for example, as I mentioned earlier, in the case of symmetry, if X relation Y, then Y relation Z. But in the case of antisymmetric property, if X relation Y is there, there may be Y relation Z and X is equals to X. That is the terminology which is respect to the antisymmetric. Fine. Now some examples we are going to discuss over here. These are very important examples. You can see what is that example. If x is equals to one set is given to you, that is 1 2 3 4 5 6 up to 10, and relation r on the set is given as, the relation r on the set x is given as r is equals to ordered pair xy where x plus y is equals to 10. So you have to find out ordered pair such a way that, what you have to find out ordered pair such a way that x comma y where x plus y is equals to 10. So we have to check which property is followed by R. You have to draw the matrix, you have to draw the graph. So these are the three things we have to do with respect to the set S by finding relation R. So as we given here set S, you can see here 1 2 3 up to 10. Then we have R is equals to, so already we have given relation. In which manner you have to find out the relation? Ordered pair x comma y, which is nothing but x plus y is equals to 10. That condition should be satisfied. So let us take here x is equals to very first element 1 and y is equals to elements from 1 2 3 4 5 6 7 8 9 10. So whenever x is equals to 1, y is equals to 1, x plus y will be equals to 2. It is not going to satisfy the condition. So to satisfy the condition for x is equals to 1, we must be take y is equals to 9. So the first ordered pair which having domain as a 1, it must gives you range as a 9, and this is the first ordered pair, that is 1 comma 9. So likewise we have to find out the ordered pairs for x is equals to 2 3 up to 10. So these are the possible ordered pairs. So whenever x is equals to 2, you can take here y is equals to 8, means x plus y will be equals to 10. X is equals to 3, y is equals to 7, x is equals to 4, y is equals to 6, x is equals to 5, y is equals to 5, x is equals to 6, y is equals to 4, and likewise x is equals to 9, y is equals to 1. So likewise you can mention here relation r is equals to 1 9, 2 8, 3 7, 4 6, 5 5, and likewise up to 9 1. So if you observe here, the ordered pairs domain and range summation is equals to 10. So that is our condition, x plus y is equals to 10. Fine. So it follows, so by the observation you can say that it follows not reflexive property, because it does not containing as it containing 10 elements, it should be gives 10 pairs which 10 ordered pairs which should having same domain and range. Means what? It should contain 1 1 2 2 3 3 4 4 5 5 6 6 7 7 8 8 9 9 10 10. But it containing only 5 5, so it is not reflexive property. Keep in mind. Yes, it does not having reflexive property. Then second one, transitive property. So what is the transitive property? If you observe here, you can check any pairs. So if you take here, let us say here, so is it transitive property is there? No, it does not having transitive property. I think so. Yes, it does not having the transitive property. And the last one, symmetric property. Yes, it having the symmetric property, because you can see here 2 8. Just wait. You can see 1 9, for 1 9 9 1 is there, for 2 8 8 2 is there, for 3 7 7 3 is there, for 4 6 6 4 is there. So it follows the symmetric properties. It does not follows reflexive property, does not follows transitive property. Hence you can say that it is not equivalence relation. When the given relation is said to be equivalence relation, whenever it follows reflexive, symmetric and transitive property, then it is called as a equivalence relation. It follows only symmetric property, hence it is not equivalence relation. So how to represent this in the matrix form? You can see here 10 by 10 matrix, because it containing 10 elements. So 10 by 10 matrix, and whenever the ordered pair is present, we have mentioned here by this one. What is this? This is 1 9, this is 2 8, this is 3 7, then this is 4 6, 5 5, 6 4, then 7 3, 8 2, 9 1. So these are the elements. Okay. So all the you can see here, no, all the diagonal elements are 1, hence it is not reflexive. So you have to check whether all the diagonal elements are 1 or not. So only a single element as a 1, so hence it is not a reflexive property. Then pair 5 5 is present, hence it is not proper conclusion. It is not a transitive property. And the last one, 2 8 having 8 2, 1 9 having 9 1, and likewise 3 7 having 7 3, 4 6 having 6 4. Hence it is a symmetric. And how to represent the graph? You have to mention all the nodes 1 2 3 4 5 6 7 8 9. So 1 9 is there, 9 1 is there. So that is the symmetric, 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 symmetric. Okay. So it having only symmetric property, it does not having reflexive and transitive property. Means the given example, this example is not equivalence relation. It does not having the equivalence relation. Now we have to see more examples. You can see here. A is equals to 1 2 3 4 5. Relation R1 is equals to ordered pair AB such a way that A minus B is a even number. That is the first relation R1. Then R2 is equals to AB where A minus B is a positive integer. Previously there was an even number. Right now you have to find out A minus B is a positive number. So we have to find out among the given two relations which one is the equivalence relation. So R1 is what? Ordered pair A comma B where A minus B is a even number. Ordered pair A minus A comma B where A minus B is a even number. So A is what? 1 2 3 4 5. So considering A is equals to 1, you can take any value of B 1 2 3 4 5. So if I take here A is equals to 1, B is equals to 1, that is A minus B is equals to 0, and that 0 is a even. You can take ordered pair 1 1. You can take ordered pair 1 1. Fine. Then A is equals to 1, increment B by 1, that is a 2. A minus B is equals to minus 1, it is not even. Then 1 minus 3, which is equals to minus 2, it is again even. Okay, so you have to take the ordered pair 1 3. Then 1 minus 4, that is minus 3, it is not even. And 1 minus 5, that is equals to minus 4, again it is a even. So 3 ordered pairs for the domain 1 we got. Then whenever, so you can see here, when the domain is 1, we got 1 1, 1 3, 1 5 as ordered pair. Similarly, by calculating for A is equals to 2 3 4 5, means we are going to change the domain as a 2 3 4 5. We will be got here ordered pair as, you can see here, 1 1, 1 3, 1 5, 2 2, 2 4 for the domain as a 2. Then whenever you are taking domain as a 3, you got 3 1, 3 3, 3 5. Whenever you got domain as a 4, 4 2, 4 4. And for the 5, 5 1, 5 2, 5, 5 3, 5 5. So these are the possible relations with respect to A minus B is a even number. Keep in mind friends, I have calculated for A is equals to 1 only. You have to write here A is equals to 2, A is equals to 3, 4 and 5, and write down these values, whatever the values I am highlighting. These are the values are calculated by using this values of X. Fine. So we got here R is equals to this ordered pair. R1 is equals to this ordered pair. Now, so that is the matrix representation. So 1 1, 1 3, 1 5. So 1 1, 1 3, 1 5. Then 2 2 is there, 2 4 is there, 3 1, 3 3, 3 5, and likewise 4 2, 4 4, 5 1, 5 3, 5 5. So that is the matrix representation. Now, so if you observe, all the diagonal elements are 1, hence it is a reflexive. All the diagonal elements, you can see here, all the diagonal elements are 1. Yes, all the diagonal elements are 1, hence it is a reflexive property. Symmetric property, you can say, when X is equals to Y, then should be Y. When X relation Y should be there, there should be alternative relation Y relation X. That is 1 3 is mapped by 3 1, 1 5 by 5 1, 2 4 by 4 2, and 3 5 by 5 3. Hence it follows symmetric property. Then transitive property. You can take here X relation Y and Y relation Z, which gives you X relation Z. So if you see here, 1 3 is there, 1 3 is there, 3 3 will get cancelled, it gives you 1 5. So if you observe the ordered pairs, 1 3 3 5, 1 5 is there, 1 3, you can see here 1 3 is there, then 3 5 is there, and by using this we can derive this 1 5. So hence it is also follows the transitive property. So you can say that as it follows reflexive property, symmetric property and transitive property, that's why the given relation is a equivalence relation. The given relation is a equivalent relation. And how to represent this in the matrix form? Simply you can see here 1, 3, 5, 4 and 2. 4 and 2. So these are the arcs which represents, for example, 1 1, yes 1 1 is there, 1 3 is there, then 3 3 is there, then here is 3 5, then 5 3 is there, then 5 1 is there. Okay, so likewise you can mention all the arcs, all the edges over here. Fine. Okay, so this one follows the equivalence relation. Now take the another example, that is R2 a comma b, where a minus b is a positive integer. A minus b is a positive integer. Okay, so a minus b, you have to take here a as a 1, b as a 1 2 3 4 5 and check. So a minus a is equals to 0, that is a positive. 2 minus 1 which is equals to 1, again it is a positive. 2 minus 2 is equals to 0, again it is a positive. Likewise 3 1, 3 2, 3 3, 4 1, 4 2, 4 3, 4 4, 5 1, 5 2, 5 3, 5 5, 5 4. So these are the possible relations. These are the possible ordered pairs for the relation R2. So it contains all x are x, hence it is a reflexive. You can see here it containing 1 1, 2 2, 3 3, 4 4, 5 5. So it is a reflexive. What is about symmetric? For every x relation y, there must be y relation x. If we take 2 1, there is a no 1 2. If we take 2 1, there is a no 1 2. Hence it does not follow symmetric property. Okay, so it is not symmetric. And transitive property, ordered pair 5 2 and 2 1, which gives you 5 1, it follows the transitive property. Means out of the three properties of binary relation, that is it follows reflexive and transitive only, it does not follow symmetric property. Hence it is not equivalence relation. Keep in mind, if the question is asked in the university examination, it is not equivalence relation. Fine. So that is the matrix representation for this. All the diagonal elements are present. So it is a reflexive property. It follows reflexive property, transitive property, but it does not follows symmetric property. So that is the notation, that is the matrix representation, and that is the graph representation. As it containing 5 nodes, you can take here 1 2 3 4 5. So that is the graph representation for the given relation. You can see here it follows reflexive property, transitive property, not follows the symmetric property, hence it is not equivalence relation. So keep in mind, these two examples are too crucial for your examination. Now the next point is composition of relation. So what is meant by composition of relation? First of all, see, these are the two examples. R1 is equals to 4a, 4b, 5a, 5c, 6a, 6c. R2 is equals to AL, AN, BL, BM, CL, CM, CN. You have to find out here R1 composition R2, R1 composition R1 converse or R1 bar. Fine. So what is meant by composition of relation? So basically in the case of composition of relation, consider two relations are given to you, x and y. You can see on the screen. If x is the first relation which is mapping from G to S, and y is the another relation which is mapping from x to H, then x composition y is equals to G tends to H. You can see here range of the first relation which is same as domain of the second. So that's why we have taken domain of the first and map with the range of the second. That is G tends to H, which is represented as G comma H, ordered pair G comma H, where G is the domain of first relation and range of H is what? Range of second relation. So you can see here is X, that is G tends to S is there. Here is Y, which gives you S tends to H, and it gives you G tends to H. This is nothing but G tends to H. That is X composition Y. What we have mentioned here, range of the first relation same as domain of the second relation. So from that you can see here you can see here R1 composition R2, which is, you can find out here R1 composition R2. So 4A, here 4 is there. Okay, so you can see here this A is same as this A. So this A get cancelled and we will be take the ordered pair as 4. We can take here this 4 and L. So you can see here this is 4L. Then this 4A and AN, it will gives you 4N. That is the 4N. And likewise 5L, 5M, 4L and 4M. So this is nothing but the R1 composition R2. Then you have to find out here R1 composition R1 inverse. It is nothing but the converse. So R1 is what? 4A, 4B, 4C, 6A and 6C is given to you. So from the R1 you can find out here R1 converse, which is same as A4. Just we are interchange here 4 and A. Then B4, C5, A6 and C6. And then applying R1 composition R1 inverse, which is same as 4, 4. You can check here 4A, A4, that is 4, 4. Then 4A, A6, that is a 4, 6. Then again, that's all. Then 4B, B4, that is a 4, 4. 4B, yes, that's all. And likewise, we have find out all these possible ordered pairs. Now, by removing duplicating ordered pair, we get the result. So if you see here, lots of duplicate pairs are there. This 4, 4 is there, 4, 4 is there. Rather than 2, we have taken here 4, 4. 6 is here, 6 is here. So we have taken this 6, 6 for the single time. And remaining are not repeated, we have taken as it is. So that's all for the composition of relation. Very important question. Keep in mind. Then, if x is equals to 1, 2, 3 and g, f are functions. Previously there was a composition of relation. Now we are looking for composition of function. So you can see here, let x is equals to 1, 2, 3 and g, f are function from x to x given by. So what we are going to mapping here? They are mapping from x to x given by. F is given to you, that is 1, 2, 2, 3 and 3, 1. And g is given as 2, 2, 2, 1 and 3, 3. Then find out function g composition f, function g composition, f composition g. So in the case of composition of relation, we are solving from left to right. In the case of composition of function, we are, see here, it is right to left read, which is opposite to relation. Which is opposite to relation. In the relation, we are starting from left, moving towards the right. In the function, we are starting from right, moving towards the left. Now, see here. You can see the relation. Okay, so before going to relation, see here, x is the one function which is mapping from A tends to B. Y is the another function which is mapping from B tends to C. Then composition of the function, that is f, y composition x. Keep in mind, y composition x, which is same as relations x composition y, and which gives you functions y composition x, which is A tends to C. A tends to C. So now functions g composition f, which is same as relations f composition g. Okay. Hence, simply find R of relation of f composition and f composition g and mention this to the function g composition f. We are going to oppositing the terms. So as we know that in the case of relation, we are moving from left to right. So there is no hesitation to find out for f of R of f composition g. So that is the result. And simply take this result for f of g composition f. So that is the result. Fine. And likewise for this, f of f composition g is equals to R of g composition f. Fine. So keep in mind that composition of function which is opposite to composition of relation, which is starting to read from right side and moving towards the left side, And in the case of composition of relation, we are starting from left side and moving towards the right side. Relatively, composition of relation is very simple. You got the idea in the previous example. We have to make the opposite adjustment in the composition of function and solve this example. Very, very important example. This one was. Now, what is meant by poset? Poset is nothing but the partially ordered set, and poset is represented in pictorial manner or diagrammatical form. It is called as a Hasse diagram. Pictorial form is called as a Hasse diagram. So what is meant by poset? The relation which follows reflexive property, transitive property and antisymmetric property is called as a poset. That is partially ordered set. When the given relation is called as a poset, when it follows reflexive property, transitive property and antisymmetric property. Generally, the poset is denoted by angular bracket p comma less than or equals to, that p is nothing but the non-empty set and less than or equals to binary relation. Okay. Rules for drawing the Hasse diagram. Nodes are represented by small circle or dot. This is the dot. Lowest level represent the least element and highest level represent the max element. So that is the poset. Poset is nothing but the relation which follows reflexive, transitive and antisymmetric property and which is denoted by ordered pair p comma less than or equals to. Let us try for these three examples. 1, 2, 3. Definitely it will be asked for the university examination. Fine. So let us take the very first example. So what is the first example? X is equals to 2, 3, 6, 12, 24, 36. That is the set given to you. And it having the relation R1. What is the R1? R1 is nothing but X comma Y, where X divide Y. Means what? Every time X divides Y, that has to check by V people. So what is the step number 1? If X is equals to 2, what we are going to do? X is equals to 3 and Y is equals to 2. Then what will be happen? Y divides X? Yes. 2 divided by 2, 1. So it divides. Means it will be satisfied for X is equals to 2 and Y is equals to 2. Then take X is equals to 2 and Y is equals to 3. So 3 by 2 is equals to 1.5. So fraction value is not allowed. So whenever X is equals to 2, there should not be Y is equals to 3. So likewise, when X is equals to 2, likewise what we are going to do? Whenever X is equals to 2, it satisfies for the Y is equals to 6, 12, 24 and 36. Because 6, 12, 24 and 36 are divisible by this 2. Then step number 2, what we have to do? Take here X is equals to 3 and Y is equals to 2, 3, 6, 12, 24 and 36 and check whether it is satisfied or not. So whenever X is equals to 3, it is satisfying for Y is equals to 3, 6, 12, 24 and 36. Fine. Then step number 3, when X is equals to 6, it is going to satisfy for Y is equals to 6, 12, 24 and 36. It is not going to satisfy for 2 and 3 because 2 and 3 is not divisible by 6. Yes. Then whenever X is equals to 12, it is satisfying for 12, 36 and 24. Not satisfying for 2, 3 and 6. Whenever X is equals to 24, it is satisfying for Y is equals to 24, not for Y is equals to 36. And whenever X is equals to 36, it is going to satisfy for Y is equals to 36. So all above 6 steps may be represented in the Hasse diagram as follows. So we have simplified by taking X is equals to 2, X is equals to 3 and up to X is equals to 36 and find out the values of Y is equals to whatever the values we have calculated. Now how to represent this into the Hasse diagram. So 2 divides 2, no issue. 2 divides 6, yes, so it is upward. Then 2 divides 12, yes, it is possible. 2 divides 36, yes, possible. 2 divides 24, yes, it's possible. Then whether 2 divides 3, no. So that's why these 2 and 3 are representing at a same level. They are representing at a same level. Then 6, which is divisible by both 2 and 3, which is placed at the next level. You can see here 2 and 3 at the same level, 6 at the next level, this 12 again at the next level. 12 separately divides 24 as well as 36, but this 24 does not divide 36, that's why this 36 is separated. and 24 is separated, and vice versa for 36 and 24. So that is the Hasse diagram for the given example. So how many nodes are there? 1, 2, 3, 4, 5, 6. Total 6 nodes are there, and number of edges are 1, 2, 3, 4, 5. So 5 edges and 6 nodes are present in the given Hasse diagram. Now the second example we are going to discuss here. Y is equals to ABC. Y is equals to ABC. Relation R2 is equals to ordered pair X comma Y, where X is a subset of Y. Very interesting question is this one. Read this question carefully. Y is equals to ABC. Relation R2 is equals to ordered pair X comma Y, where X is a subset of Y. X is what? Subset of Y. Means what? You have to find out all the possible subset of Y. So you can see now we have to find out all the subset of Y, that is P of Y. Means what? We have to find out this by finding the power set. So this is nothing but P of Y, which is nothing but phi single A, single B, single C, then AB, AC, BC and ABC. So these are the possible subsets. So total 8 possible subsets are there. Now we have to work on this relation R2. So whenever X is equals to phi, absolutely this phi is a subset of this Y is equals to phi. This phi is a subset of this A, phi is a subset of B, phi is a subset of C, subset of AB, subset of AC, subset of BC and subset of ABC. Means what? Definitely this node phi will be towards the bottom of this all possible supersets. Then next one. Whenever X is equals to A, Y is equals to A, Y is equals to AB, Y is equals to AC and Y is equals to ABC. So these are the possible subsets. Okay. And likewise X is equals to B, Y is equals to B, AB, BC and ABC. I hoping that you will be get this. X is equals to C, Y is equals to C, AC, BC, ABC. X is equals to AB, Y is equals to AB and ABC. X is equals to AC, Y is equals to AC and ABC. And likewise this one. And the Hasse diagram for this one is belongs to follow. This is the phi. Phi is a subset of this A, subset of this B and subset of this C. So phi is to the bottom level of this ABC. And this ABC are at the same level because A is independent than B, B is independent than C and C is independent than A, and they are not subset of each other. They are independently working. So you can see here this A, B is presented over here and C is presented over here. Then next one, we are joining this B and A together to got this AB. Okay, so AB is a superset of this A, B and phi. This AC is a superset of this A and C. Then this BC is a superset of this B and C. And all these AB, AC and BC are not superset of each other. They are not subset of each other. So that's why they are located at a same level. This is your level number 0, this is our level number 1, this is your level number 2, and finally ABC is supremo, you can say, or superset, which is at a level number 3, okay, which is nothing but the superset of all these sets. All these sets superset is there. Okay, so that's all for this example. Very interesting example. Please go through this solved example, you will be get the idea. Now the next example, R is equals to, again it is the example of Hasse diagram. R is equals to AB and we having the relation A divides B on S is equals to 1359, 15, 45, 90. Fine. So now we have to find out when A is equals to 1, whether it going to satisfy or not. Yes, whenever A is equals to 1, definitely this 1 will be divided 1, 3, 5, 9, 15, 45, 90. No issue. It will be divided all these terms. Whenever A is equals to 3, it will be divided itself 3, 9, 15, 45 and 90. Whenever A is equals to 5, it will be divided 5, 15, 45, 90. Please observe the pattern. It does not divide 1, 3. Likewise, A is equals to 9, B is equals to 45, 90. And likewise, A is equals to 19, B is equals to 90. So finally, you may got the idea here. A, that is 1 at a very low level or bottom level, 3, 5 at the next level, then 9 and 15 at the same level, 45 to the next level, and 90 at the next level. So that is the level number 0, level number 1, level number 2, level number 3, and level number 4, that is the supremo 90. So that is the Hasse diagram. How many nodes are there? 1, 2, 3, 4, 5, 6, 7. 7 nodes are there. And how many edges are there? 1, 2, 3, 4, 5, 6, 7. 7 node and 7 edges are there. So that's all for the Hasse diagram. Very important questions you have to keep in mind. You have to solve this example also. Now the next point is, what is meant by function? So if you see, the function is nothing but, let x and y be the two sets. The relation f from x to y is called as function if for every x is belongs to x, there is a unique y belongs to y and x comma y is belongs to f. Means, for example, if two sets are there, x comma x and y, these are the two sets, then x should be mapped with the elements from y. Okay, once, then it is called as a function. So in the diagram you can see here, in the diagram you can see, this is the notation for function. Here this x is called as a argument, and this y is called as an image. This one is called as an argument, and this one is called as an image. Fine. So keep in mind this diagram. Okay, this x is called as an argument and y is called as an image. So types of function, I am taking important points only. Scaling function. Scaling function means it is represented by you can see here scaling. You know that scaling fan. You can see the notation which clearly mention it is a scaling function, which gives you the upper bound. So upper bound of 3.75, that is a 4. Upper bound of minus 4.8 is a minus 4. So these are the scaling function. What is meant by floor function? So in the case of floor function, you can see here that is the lower bound. So lower bound of 3.33 is a 3, and lower bound of minus 4.8 is a minus 5. That is the scaling and floor function. So already we have seen what is meant by composition of function. You can go through that. Then not necessary to take this. Yes, types of functions. So basically there are three types of there is a three types of function. First one is the injective, which is also called as a one-to-one mapping. Then second one is the surjective, that is called as a onto mapping, and the last one is the bijective, which is called as a one-to-one onto mapping. And this one is not a valid function. Yes. So that's all for the chapter number 3, that is functions and relations. So what we have seen in the functions and relation, I am revising here. The very first point is what is meant by binary relation and properties of binary relation. So properties are 5 properties: reflexive, symmetric, transitive, antisymmetric, and irreflexive. Then we have seen one example. We have to find out whether it follows reflexive property, symmetric property, and transitive property or not. And by using that, we have to check whether it is a equivalence relation or not. Then we have drawn matrices and graph. Then we have seen what is meant by equivalence, what is meant by inequivalence. Then we have seen what is meant by composition of function, composition of relation, and different types of functions. So basically, in the case of function, we have seen what is meant by surjective function, what is meant by bijective function, what is meant by injective function, what is meant by scaling function, and what is meant by floor function. So these are the points you have to keep in mind. Also, we have seen what is meant by poset. Then we have seen Hasse diagram and how to draw the Hasse diagram from the given posets. So that's all for the unit number 3. That is functions and relation. Thank you so much for patience listening.